t, we'll take this equation, solve this equation for t, and we get the final velocity minus the initial velocity, all equal to, divided by acceleration, that equals time. That's from this equation. From this equation over here, how do we solve this equation for t? We would say, I'm going to do it right here. Let's multiply by 2. We get 2x equals the sum of these times t. So that if I solve for t, I would get 2x divided by the sum of these. That's equal t. Okay, so notice that's the same thing as this over here. So this expression is from this equation up here. This expression is from this equation. But we've solved, so this t has to equal this t. So I'm going to slide these things together. I'm going to say these two things are now equal to each other. This expression equals this expression. I'm going to slide this over a little bit. 2x divided by the initial velocity plus the final velocity. Okay? Now, how do we solve this equation? Let's take this term. Well, one way to do it, do you remember cross multiplying? If you have a over b equals c over d, we can cross multiply. A times d equals b times c. You remember that. We can do the same thing here. Let's cross multiply these two terms. This times this equals this times this. So the first two terms, the final velocity minus the initial velocity times, and I'm going to take these two and I'm going to just flip them just for fun. The final plus the initial. It's the same thing, I just change the orientation. Equals 2 x times a. Okay, I'm going to make it easy to read, I'm going to erase this up here. I'm going to come up here, okay, and I'm going to multiply these two together. Vf of v final squared. Notice that this term and this term, we have vi minus v final, a minus term. Then we have v final minus v initial, a plus term. They cancel each other out. Basically, we get the initial velocity times the final velocity. That's the inner term. And then the outer term is plus the same initial velocity times the final velocity. Notice these terms add up to 0. So we're just going to ignore these two terms because they add up to 0. And then we get the final term, which is minus v squared. Minus v initial squared equals 2x. I'm just going to switch these. 2ax. I'm going to solve for the final velocity. The final velocity squared equals the initial velocity squared plus 2ax. This now is equation 215 in your book. Okay, so, and we have now just derived this equation 215. How do we do it? It's from the original two equations, and then we eliminated time. Notice there's no time in any of this equation. So really, the rest of the chapter on all the problems is learning how to use these equations. So in this chapter, Again, I'm going to go over these equations that you need to know, and they're all listed in this on page 47, that the velocity is equal to the change in distance over change in time. The acceleration is equal to the change in velocity over change in time. The final velocity is the initial velocity plus acceleration times time. And then the two derived equations, that the distance, the final velocity squared equals the initial velocity squared plus 2ax, and that the distance, the displacement, is equal to the initial velocity times t plus 1/2 at squared. The whole rest of the chapter is really learning how to solve problems with these two equations. So really the rest of the time what we're going to do is spend it just on going over different types of questions, different types of problems. You need to memorize these equations. After you use these equations, for especially these two, after you use these equations, you should become quite comfortable with them. You should, and hopefully have them memorized. You'll have to have them memorized for the test. So, okay. As an example, let's go over on page 48 and page 49. There's an example problem. Okay, a car is traveling down a road at 27 meters per second. So that means the car has an initial velocity of 27 meters per second. Okay, and the car suddenly sees a cat on the road and ahead, and he slams on the brake, and he deaccelerates and he gives the rate. He deaccelerates at a rate of 7.5 meters per second squared. Now, if think about this, if he deaccelerates, he puts on the brakes, is his acceleration positive or negative? His acceleration actually is negative because he slows down. He has to have a negative acceleration. If the cat is 50 meters away, he starts from here and he goes out 50 meters. Okay, here's the cat. If the cat stays there, will the cat get hit by the car? Okay, that's the problem we need to solve. So, okay, the question is, if here's a car. The question is, by the time the car moves 50 meters, will the car velocity, now the cat doesn't move, will the final velocity be 0 or not? Okay, so we're going to look at that. Now, one thing we're going to say is we can say, well, what is the distance? Let's solve for this distance x, where, think of it this way. Let's solve, one way to solve it, there's several ways to solve this problem, of course. One way to solve it is to solve for the distance when the final velocity is 0. If that distance is less than 50 meters, cat's safe. If the distance is greater than 50 meters, then the car will basically run through the cat. Do you understand? Okay. So how do we do this? We can use the definition of acceleration. Acceleration is a change of velocity over the change of time. Okay. But notice here, well, notice here we don't know anything about time. So although we could use this and we could solve for the time, it may not help us. So let's think of one of those equations we have where is time independent. We have one of those. We will come back to this equation now. Think of this equation. The final velocity squared equals the initial velocity squared plus 2ax. Okay? There's no time in this equation. So we have the final velocity. We know what this is. The final the initial velocity here, we're going to plug in 27 meters per second right into the initial velocity. The final velocity, we want to plug 0 into here because we want to solve the distance when the final velocity is 0. Okay? And we want to solve for distance. So we're going to set this equal to 0. Okay? So 0 equals the initial velocity squared plus 2ax. Whenever most students would want to go ahead and start substituting numbers into this equation, and I say, wait, always solve for what you're trying, always solve by algebra what you're trying to look for, and then plug in. So let's solve this equation for x. We get minus vi squared equals 2ax. Solving for x, x equals minus vi squared all divided by 2a. Okay, so over this side, I have minus v. Now the signs in this case are important. So we have minus, the initial velocity is 27 meters per second. We're going to square that, and we're going to divide it by 2 times the acceleration. The acceleration is a negative 7.5. Negative 7.5 meters per second squared. Notice the minus signs cancel out, just like they should. And if I take my calculator, I get 27 squared, check me on these numbers, divided by 2, divided by 7.5, and I get x equals 48.6 meters. So, what does this mean? This means that the car comes to a stop at 48.6 meters, just a little before 50 meters, so the cat is safe. Okay? Thank God. So, okay. Now, is this the only way to solve this problem? No, it's not. There is another way to solve it. As typical with these kinds of problems, there's there's usually 2 ways to solve a problem, sometimes even more than that. So what is one other way of solving this problem? Okay. Another way is this. Go back to the equation that we started with. Acceleration equals change in velocity, or the final velocity minus the initial velocity divided by delta t. Okay. Again, let's solve this for where the final velocity, let's say we want the final velocity to be exactly 0. The car stopped. What we're going to do is we're going to solve for the time. Okay, so delta time, the time lapse from the initial velocity to where it stops. The time will be equal to the final velocity minus the initial velocity, all divided by acceleration. The final velocity is 0, minus the initial velocity is 27 meters per second, all divided by the acceleration, which is a minus 7.5 meters per second squared. Notice the minus cancels out like it should, and we take a calculator and we say 27 divided by 7.5, and we get 3.6 seconds. So the car took 3.6 seconds to stop. Now that's just a time, but how far did the car travel in that 3.6 seconds? It traveled the distance that's equal to the average velocity times time. Okay? The average velocity times time. Well, what's the average velocity? The average velocity is simply the initial velocity plus the final velocity, all divided by 2. So it's 27 plus 0 all divided by 2, which is, what's that? 13.5 meters per second. Okay, so just midway between 27 and 0, that's the average velocity. So we come in here and we say the distance traveled is the average velocity times time. So it's the average velocity is 13.5 meters per second, all multiplied by 3.6 seconds. We're taking that time and plugging it right in here, and we get, let's see, 13.5 meters per second times the time is 48.6 seconds. Excuse me, that's meters. Meters. Which is the same answer we got before. So notice there's several ways you can get these answers, but the key is in this case you solve for the time, and then you could use the average velocity. Okay, so hopefully that's clear. Let's see. Okay, if we go on further to into the page 50, 55, and 56, we start talking about free fall. Okay, and this is toward page 60 and beyond is where it comes to the end of the chapter. So free fall, where a lot of our questions deal with free fall, and in free fall kinds of situations, it would be like where we take a ball and then we just drop a ball and it just falls by gravity. Free fall means it's falling freely. Another type of this problem would be where we actually give it an initial velocity and then it falls back down. So the initial velocity sends it up, but gravity pulls it down and it comes back down. So all of these types of problems are solved by all of these equations too. So let's, an example of this is on page 56. on page 56, there's an example 2.5. And let's go ahead and do that problem. So this is on page 56, example 2.5. A penny is dropped off a tall building. The tall building is 0.15 kilometers tall. If the person holding the penny holds a penny still, what will be the velocity at the instant that it hits the ground? In fact, let's do two things. Let's calculate the velocity and let's calculate the time it takes. Okay, so when you get a problem like this, first thing I always tell students to do is to draw a picture. So here's your picture. Here's the ground. Here's a tall building. And here's you up here, and you're dropping a penny. And the distance you drop it from, the length of the height of this building, is 0.150 kilometers, which is, of course, 150 meters. So it's 150 meters tall. And the question is, actually, what is going to be the final velocity when it hits the ground, right here? We're going to ask that. And also, let's ask the question, what's the length of time it takes? Also. Now, how do we solve this? The key here is knowing two things. One is that the initial velocity is 0. We just take the penny and we just release it, so the initial velocity is 0 and it starts to drop. And the other key is, what is the acceleration of gravity? Acceleration of gravity is 9.8 meters per second squared. If we convert this to English units, it would be 32 feet per second squared. These numbers you just need to memorize. Now, later on in chapters, about chapter 5 or 6, we will actually derive this number. But for right now, we can't do it. We don't know enough about gravitation to be able to derive this yet. But actually, in about 3 chapters, you will actually derive what this acceleration number is. Is this number of 9.8 meters per second squared and this number of 32 feet per second squared, is this an exact number? No, it's not an exact number. It's only an approximate number. Does it change all over the Earth? It does change all over the Earth. In some places, it's a little bit higher than 9.8 meters per second. It may be 9.82 or 9.85. In some places, it's actually 9.7 something. So this fluctuates. It also depends on how high, if you're in the mountains or like on the top of a tall mountain, it will be a little bit less. In Death Valley, it may be a little bit more. But not only does it depend on where you are in the mountain on the Earth, maybe you're on a mountaintop or in a valley, depends on the mountain, your distance from the center of the Earth, but it depends on the density of the Earth. And the density of the Earth is not uniform all over. And so this is one thing geologists and geophysicists study. And one thing they note is that the more dense the rock is, the more massive it is, and the higher the acceleration of gravity tends to be in those localized areas. So actually, there's a lot of kind of geology and geophysics involved with exactly what this number is. But we'll save that for another discussion. So, get back to, well, let's see. That's right, we're working on this problem. The initial velocity of 0, and we want to solve what the final velocity is and what the time is. Okay. We're going to do this as many different ways as we can. Okay. Think of our equations. Well, we have this equation that goes like this. X equals the initial velocity times time plus 1/2 AT squared. Okay? Can we use this equation? Actually, we can. We know that the initial velocity is 0, don't we? That means this whole term is 0 and goes away. So we're left with that the distance dropped, this is x, this distance from here to here is x, the distance dropped is 1/2 AT squared. Okay? So we know what x is. Actually, we know what a is. We know the a is the acceleration of gravity, so we can solve for t. So we can take this equation and let's solve for t. It would be 2x equals AT squared, or 2x divided by a equals t squared. So 2x over a square root of is time. Okay? So I'm going to take this and let's substitute in the numbers we know. We have 2 times x is 150 meters divided by 9.8 meters per second squared. Okay, and the square root of that. And let's look at the units here. That's very important. Notice the units. I'm going to write this up here. We have meters divided by meters per second squared. Notice that all the square root of, notice that the meters will cancel out, giving 1 over seconds, which actually is the same thing as second squared. Square root of the second squared is seconds. So this has units of seconds, which it should because this is a time. So we take a calculator. We say 2 times 150 divided by 9.8, and then we take the square root of that. And I'm going to round off to 2 significant figures because 9.8 is 2 significant figures, and I get 5.5 seconds. So that tells us that when you drop a penny from 150 meters up, it takes 5.5 seconds to accelerate down and to actually hit the ground. 5.5 seconds to hit the ground. Okay? But what is the final velocity? Well, actually, we solve the time first. The final velocity, again, there's a couple ways we can do this. Think of this equation that the final velocity squared equals the initial velocity squared plus 2ax. We know that the initial velocity, again, is 0, so that the final velocity equals 2ax and the square root of 2ax. Okay, so let's put in the numbers. 2 times 9.8 meters per second squared times 150 meters, square root of all of this, and we get 2 times 9.8 times 150 square root of, and we get 54 meters per second. Now notice that here we had meters, meter times meter, that's meter squared divided by second squared, second squared, all square root of, so we'll get meters per second. So notice when you do these, a good check is to make sure that the units cancel out and give you the right velocity units that you should have. Okay, so this is the final velocity. The final velocity is 54 meters per second squared. Now, what is a good check? If you have all this information, a good check is to say this. Remember that the acceleration equals to the change in velocity over the time. So that's the final velocity minus the initial velocity all over time. Okay. So here's another way. So we can use this acceleration times time equals the final velocity minus the initial velocity. And this is actually a good check to see if this is right, and if our time, what we calculate is right. The initial velocity we know is 0. So if I take 9.8 meters per second squared, multiply it by 5.5 seconds, it should become equal